We'll now move to the third question. So third question. Here they have not given the configuration of the chopper. Instead they have just mentioned there is a chopper. Remember, chopper is same as a converter. They've shown a chopper supplying an inductor to the load. They have given this voltage as 12 volt. They have given the inductor as a 20 millihenry, and they have also shown a 5 ampere charging current of the inductor. And this voltage they have written as VDC. With this, they have also given the waveform of the output voltage. So the waveform VO is given by them, and they have given this as this. They have written as VDC, and they have written here 60 volt. Then they have mentioned the time. This they have written as 200 microsecond. This time is 200 microsecond, and this whole time they have written as 1 millisecond. So this is the question which is given, and it is asked in the question to find what is the peak-to-peak ripple in the charging current. That is, what is the peak-to-peak ripple in this 5 ampere. This 5 ampere is basically the current through the inductor. So they are asking to find what is the peak-to-peak ripple in the inductor current. So again, similar to the previous two questions, here also we have to directly start using the formula. So we have the solution. I'll write it here. Solution: delta IL is equal to VI. Now VI is VDC, and in this graph VDC they have given as 60. So this is 60 minus VO. VO they have shown here as 12 multiplied by T on. T on is from here 200 microseconds. 200 into 10 to the power minus 6 divided by L. L is 20 millihenry. So 20 into 10 to the power minus 3. Now, how did we identify that we have to use this equation only? How did we identify this is a buck converter? By seeing this voltage. This VDC was given as 60 volt, while the output is 12 volt. That means the output is smaller than the input. So this is the case of a buck converter. That's why we have used this equation. So 60 minus 12. So we have 48 here, multiplied by, this becomes 10 raised to minus 3 only, and this becomes 10. So effectively this and this we get 10 raised to minus 2, which is equal to 0.48 amperes. So this is what is asked, and that is the change or the ripple, a peak-to-peak ripple in the charging current, that is delta IL. We'll now move on to the next question. So question number 4. This is not a numerical. Here they have given a chopper configuration, and they're asking us to find out what kind of chopper is it. So what they have given is this. There is an input voltage V in. The switch that they have shown is a single pole double throw switch, and then an inductor, and they are showing a load. They're showing a load, and they're giving this voltage as VO. So they have asked to find out what kind of configuration is this. So if you see here, this is a single pole double throw switch. So for some time this P will be connected to A, and for some time it will be connected to B. So when P is connected to A, we'll write the solution. When P is connected to A, the circuit is like this to the load. P is connected to A. And the second case, when P is connected to B, it is this kind of circuit. So we have directly inductor and the load. If you see, this is what happens in the case of a buck converter. When the switch is on, through the supply, inductor charges and and current flows through the load. And when the switch is off, the inductor discharges through the load via the diode in the buck converter. So here, instead of diode, you can see it is a closed circuit and the current is flowing through the inductor to the load. So this is same as the buck converter. So in this question was asked to find which configuration is this. So this is a buck converter. We'll now start with the next question, question 5. This will be the last numerical that we consider for buck converter. Then we'll move on to the next converter, which is a boost converter. So question number 5. The circuit that they have given is switch, not inductor, and the load. They have given the input voltage as 100 volt. The load they have given as 10 ohms. And they have also given that the duty cycle of the switch is 0.8. What they have asked to find is the average diode current, that is ID. If we consider this as D, then this is ID which they asked us to find. So we now have to find a solution for this. Now, the diode, when the switch is in the on condition, the diode was reverse biased. So there was no current flowing in the diode. So if we make the waveform of the diode current, ID, if we make, the current in the diode flows like this in the off condition. So this we have considered as ID. Okay, and this is the time. So when the switch is in the on condition, that is a T on time, the diode is reverse biased. So the diode current will be 0. Next, when the switch is in the off condition, sorry, this is T. So this was T off. When the switch is in the off condition, this gets forward biased because of the inductor current. So current will flow in this diode. Now this current is same as the inductor current. So we have ID, which is same as the inductor current, IL. If you remember, we had seen the inductor current will be same as the output current. You can also see here, this is the current flow. So this diode current is same as the inductor current, which is also same as the output or the load current. So this is equal to IO. So this is what the diode current waveform is. Now, next we have to find what is the average diode current. So from this waveform, you can find the average current. The average current will be something like this, which will be ID. Writing the formula for the average current waveform, so ID will be IL, which is same as I naught, only for a time duration of T off, divided by the total time T. Now you have to find all these values. So I naught we can find by V naught by R. So we have I naught is equal to V naught by R. R is the load. So what is V naught? V naught is not given to us, but we know V naught is equal to D into Vi. So we can write here as D into Vi by R. So what is D? D is given as 0.8 into V is 100 and R is given as 10. So we get this as 8 amperes as I naught. So we got I naught as 8 amperes. Next we need to find T off. Duty cycle is given to us by T. Okay, so T off we can write as if you from this equation, this T was T on plus T off. So we could get either T on is equal to dt and T off is equal to 1 minus d into t. So this t, 1 minus d into t, when we substitute here, this is 1 minus d into t. So this t and this t gets cancelled off and we get id is equal to I naught, which is 8, multiplied by t and t gets cancelled, so it is only 1 minus d, which is equal to 8 into 1 minus 0.8. 1 minus 0.8 is 0.2. So 8 into 0.2, which is equal to 1.6 amperes. So this is the average diode current.